The study of Calc 1 was the study of functions who took real numbers as inputs and spit real numbers back as outputs. If we happen to have two of these scalar functions, say s and r, then we could take the outputs from one of the functions and stick them in as inputs of the other functions. So we could take an input value t, we could plug it into the function s, and then take that output value and plug it into the function r. We called these things compositions. And probably the single most important derivative rule was a rule for handling a composition. If you wanted to take the derivative of the function r of s of t, one function stuffed inside of another function, we called this derivative property the chain rule. And what it said was, you differentiate the outer function, blanking out the argument, and then you fill in the argument, which is s of t, and you multiply by the derivative of the inside function. So we called this the chain rule. The derivative of the outside function times the derivative of the inside function. But now we have more types of functions. We talked about vector-valued functions, which were functions whose inputs came from the real line, but whose outputs were vectors, so a value in R2 or R3, or more generally in Rn. And most recently, we've talked about functions of several variables. Which are functions whose inputs are ordered pairs or triples, or in general from Rn, but whose outputs are single real numbers. Remember that each one of these guys had their own special derivative concept too. The derivative concept for a scalar-valued function was, well, a scalar. The derivative concept for a vector-valued function was this thing that we called the velocity vector. So this curve at a point who pointed in the direction you were going with a specific speed. And for a function of several variables, the derivative concept was the gradient of the function, which was another kind of vector, but it was one that somehow counted slopes in many directions simultaneously. So we could ask ourselves, what kind of compositions can we make from these sorts of functions? And what compositions would have a chain rule? So let's start off with real inputs. Suppose you had a real number t. Well, we could plug a real number like that into a scalar-valued function, the kind of thing we did in Calc 1. So the outputs would now be real, but those real outputs could be now the inputs for a vector-valued function. So we could take a vector-valued function of a scalar function, and we could ask, what would be the derivative of something like this? Well, we already saw this in the vector-valued section, that the derivative of something like this is you differentiate the vector-valued function to get a velocity vector, and then you would multiply that by the scalar derivative, s of t. What's another way that we could compose things? Well, we could maybe start off with a point in Rn, and right now I'll just draw it as a point in two dimensionals in R2. So if we had an input in Rn, we could stick that into a function of several variables, f. The output would be real, which means we could stick that into a scalar-valued function. So we could look at s of f of xy. This is now a function of two variables. It had two inputs. And so we could talk about taking its gradient, which is the appropriate derivative concept. And we saw yesterday that the gradient of something like this, well, it will be the derivative of the outer function. The outer function is a scalar valued, so it'd be f prime of f of xy. Multiplied, this is a scalar, so we'll multiply it by the gradient vector of the inside. So before looking at one last composition, notice the similarities each time. In each one of these, we take a derivative of a composition, and it's always the derivative of the outer function evaluated at the inner function times the appropriate derivative of the inner function. This is the heart and soul of what makes a chain rule a chain rule. Now let's take a look at one last composition. Imagine that you started off with a real input value t. You could plug that real input value into a vector-valued function. So now your output would be a value in Rn. You could then take that Rn value and stick it into a function of, say, 2 or 3 variables. So the resulting composition is a function who takes one variable as an input and spits one variable as an output. So it's a scalar function. So we could take its scalar derivative, dt, dt. What would its scalar derivative look like? Well, if we're following the pattern of the chain rule, it should be the derivative of the outer function. The outer function is f. F is a function of several variables, so it ought to be the gradient of f evaluated at the inner function. Then it's always times the derivative of the inner function. Well, the inner function is v. Its derivative is the velocity vector. Unfortunately, I can't leave it like this because this is a vector, and this is a vector. And you can't just multiply vectors. We have specific products. But remember, this right here is supposed to be a scalar. It was a function of one input, one output. So how do you take two vectors and turn them into scalars? Well, you dot them together. And it turns out that this formula, which we've sort of deduced by following patterns, is actually correct. In fact, this last formula is sometimes called the multivariable chain rule. And we can simply add it into our collection of lots of chain rules. Verify the chain rule if f of xy is equal to x squared y and v of t is equal to the cosine of t times e to the 2t. So the multivariable chain rule says that if we were to go and take v of t, a function of a vector valued function, and plug it into f, a function of two variables, and then differentiate that, that should be the derivative of the outer function, which is the gradient of v of t, dotted with the derivative of the inner function, which is the velocity vector v of t. So what we're trying to do is we simply want to check that this formula works out. So let's attack it in pieces. Let's focus on the left-hand side first. So the left-hand side, we need to first work out f of v of t. So that would be f of, now v of t is equal to cosine of t e to the 2t. So if we plug that into our formula for f, f is equal to x squared, so cosine of t squared, times y, e to the 2t. And now we simply want to differentiate that. So if we take the derivative of f of v of t, then we would get, well, let's see, we'll use the product rule and the chain rule here. We would take the derivative of the first piece. The derivative of blank squared is 2 times blank times the derivative of blank by the scalar chain rule. That's the derivative of the first part times the second, plus the first part, which is the cosine of t quantity squared, times the derivative of the second. The derivative of e to the 2t is e to the 2t times 2 by the scalar chain rule. So if we were to clean this up, we're going to have, let's see, negative 2 e to the 2t times the cosine of t times the sine of t, plus 2 times e to the 2t times the cosine of t quantity squared. And notice that there's a 2 e to the t cosine t that I could pull out from both of these pieces. And so I have 2 e to the 2t cosine t. And when we pull it out from the second piece, we'll just have a cosine of t left over. And from the first piece, we'll have a negative sine of t. And so there's the derivative of f of v of t. So now we have the left-hand side of this equation right here. Now let's focus on the right-hand side of the equation and see if it matches. So first, let's work out the gradient of f at v of t. So the gradient of f at v of t is going to be, well, let's first work out the gradient of f. The gradient of f is going to be the vector whose first component is the derivative of f with respect to x, so 2xy, and whose second component is the derivative with respect to y, x squared. And so now we can plug in the point cosine of t e to the 2t, the gradient of f evaluated at v of t. So that's going to be the vector 2 times x times y, and the second component will be x quantity squared. On the other hand, we need to work out v prime of t. Oops, I forgot the prime this whole way through. V prime of t. Well, if we differentiate this vector-valued function, the derivative of the first piece is negative sine of t, and the derivative of the second piece is e to the 2t times 2. And so that gets us the vector negative sine of t, 2e to the 2t. And so finally, we need to take the dot product of these two expressions, f of v of t, dotted with v prime of t. So we'll take the vector 2e to the 2t cosine of t, cosine of t quantity squared, that's the gradient bit, and we'll dot it with the vector negative sine of t times 2e to the 2t. And so when we multiply across the top, we're going to have this times this, which will be negative 2 times e to the 2t times the cosine of t sine t. And then we'll multiply across the bottom row, which will get me 2e to the 2t times the cosine of t squared. Now, both of these pieces have a 2, an e to the 2t, and a cosine of t. So if we pull that out, we're going to have 2e to the 2t cosine t. When we pull it out from the second piece, we're just going to have a cosine left over. When we pull it out from the first piece, we're going to have a negative sine of t left over. And this becomes the right-hand side of our equation. And we see that the two sides do in fact match. Multivariable chain rule is kind of a cool formula because it relates the three different types of derivatives we've talked about so far. But it is sort of a clunky looking formula to use and can be rewritten in a form that does make it slightly easier to remember and slightly easier to apply. Let's suppose right now that f is a function of two variables. So let's say that f has the variables x and y. Let's also say that v of t has to therefore be a function, a vector valued function in R2, and let's write its components as x of t, y of t. So when we actually look at f of v of t, that's the function f of x of t, y of t, we can really think of f as a function of one variable. When we compose it, he's really a function of f of t. And so the left-hand side of this equation, we can write as the derivative of f with respect to t. And I'm using the d's because this is a scalar valued function. Now, on the right-hand side, how do you get a hold of the gradient of a vector? Well, the gradient of a function is the partial derivative of f with respect to its first variable and the partial derivative of f with respect to its second variable, since f has the variables x and y. On the other hand, how do you find a velocity vector? Well, you differentiate each one of the components separately. So you take the derivative of the x component and the derivative of the y component. And so by being a little bit lazy with the symbol set, by not writing every one of the insides down, essentially by hiding the actual variable t, I can write the formula like this. Now I'm going to admit that this isn't quite an improvement, but let me expand the right-hand side out. So we can write this as df dt is equal to, multiplying across the top, del f del x times x prime of t plus del f del y times y prime of t. And that's a little bit easier to remember, but wait. Each one of these guys is a scalar function, one input, one output. And so I could write their derivatives in terms of the dd notation. This first guy would be dx dt, and the second guy would be dy dt. And this new formula has exactly the same meaning as the old one, but it's got sort of a nice pattern to it. To take the derivative of f with respect to t, what we do is we take the derivative of f with respect to its first variable times dx dt, then df with respect to the second variable y, dy dt. There's this almost pseudo-cancellation going on here where I sort of canceled the dx's or the dy's, and I can see the df dt's sort of lying in wait there. So it's a nice mnemonic for remembering what's going on. This guy is also a lot of times called the multivariable chain rule. Now, what had happened if f was a function of 3 variables instead of 2? How do you think you'd modify this? Well, hopefully you can see what the pattern is. The derivative of f with respect to t is df dx dx dt, df dy dy dt, and so the next term should be df dz dz dt. And in fact, this is the 3-variable version of the multivariable chain rule. So let me sort of show you how this version of the chain rule can be used to solve some complicated derivative problems. compute the derivative of the function s of t equals the square root of t plus 1 over t squared plus 3 times the quantity s sine cubed t. Now, on the one hand, this is just a straight-up derivative problem. We could go and take this function s of t, we could prep it as t plus 1 to the 1/2 power times t squared plus 3 to the negative first power times the sine of t raised to the third power, and then we can work our way through the product rule twice and the chain rule thrice, and be at some version of this answer. However, that's not the way I want to do this one right here. What I want to do is I'm going to sort of add an intermediate step here. I'm going to talk about the function s of three variables, x, y, z. And this function is going to be x to the 1/2, y to the -1, z cubed. And I didn't pick this at random. Hopefully, you'll see that there was a little bit of method to my madness. I'm also going to talk about the functions x equals t plus 1, y equals t squared plus 3, and z equals the sine of t. And I could think of this as a vector-valued function. And so I'm taking my vector-valued function's components and I am plugging them into my function s. And so we're doing a composition. So I could apply the chain rule. The chain rule says if I want to take the derivative of s with respect to t, it's a function of three variables, so it should be del s del x dx dt plus del s del y dy dt plus del s del z dz dt. So let's do this. Let me first work out these three partial derivatives here, because I have the formula for s right here. The partial derivative with respect to x will be 1/2 x to the -1/2 times y to the -1 times z cubed. The second partial derivative will be, with respect to y, is negative x to the 1/2 y to the -2 times z cubed. And then the derivative with respect to z will be 3 times x to the 1/2 times y to the -1 z squared. Next, I'll work out these three derivatives with respect to t. The derivative of x with respect to t is 1, the derivative of y with respect to t is 2t, and the derivative of z with respect to t is cosine of t. And so I'll add these three expressions up. That's what the multivariable chain rule says. Notice that there's some things that I could factor out of this thing. I could factor out an x to the -1/2, because there's a power of x common to everybody, and -1/2 is the smallest. There's also a y to the -2 common to everybody, and there's also a z squared common to all these terms. So I could pull them out. I'm also going to pull out the fraction 1/2, just so I can eliminate some fractions. So when I pull these out of the first piece, the 1/2 is gone, this is gone. I have only a single z left over, and y to the -2 factored out of y to the -1 leaves a y. So this first piece will leave me with a yz. In the second piece, the minus will be left behind. If I factor a 1/2 out of a 2, that's going to leave me with a 4. 4 times 1/2 is 2. I've pulled out an x to the -1/2, which will leave me with one x left over. Y to the -2 has been pulled out, and z squared has been pulled out, so it's going to leave me with a z and then a t. And finally, in this last piece, if I pull a 1/2 out of a 3, that leaves me with a 6. I pulled x to the -1/2 out. That's going to leave an x to the whole power. We pulled y to the -2 out, which is going to leave a y to the whole power. We pulled z squared out, and we're going to have a cosine of t left over. And so there's the derivative according to the multivariable chain rule. Of course, I can't box this, because, just look at the original problem. The original problem had only one variable in it, t. It didn't have x's and y's and z's running around. This answer is no good for that problem. But remember, we know the formulas for x and y and z. We made them to start this problem off. So if we substitute in, we're going to get 1/2 x, which was t plus 1 to the -1/2 power, times y, which was t squared plus 3 to the -2, times z, which was the sine of t, quantity squared. We've pulled that out of yz, so y is equal to t squared plus 3 times sine of t, minus, we have a 4 and a t already, x is t plus 1, z is sine of t. And then we have plus 6 times x, which was t plus 1, times y, which was t squared plus 3, times the sine of t. And check that out. We have a derivative in t, and it's already been pre-factored for us because it was far easier to factor it with the x, y's, and z's in. There's maybe one round of cleanup I could continue with right here. I do have these two terms with sine t's in front. We have t squared plus 3, and then we have negative t to the squared minus 4t. So if I were to do one last round of cleanup, we would have 1/2 t plus 1 to the minus 1/2 power times t squared plus 3 to the minus 2 times the sine of t quantity squared times, we have t squared minus 4t squared, so minus 3t squared minus 4t plus 3 times the sine of t, so those are the coefficients connected to sine, plus, and then over here we're going to have 6 times, well, I guess I could FOIL this thing out. That would get me t cubed plus t squared plus 3t plus 3 times, oops, I say that wasn't sine, that was cosine of t from the previous line, times the cosine of t. And so this bad boy right here would be our answer. Whew! Imagine trying to do that longhand. If f of xyz is xy squared times e to the xz, and x is equal to 2 plus 3t, y is equal to 6 minus t, and z is t squared, compute the derivative of f with respect to t at the value 1. So notice that even though f is a function of x, y, z, we're asking for the derivative with respect to t. So the problem is sort of implying that we want to stick these values in. So we're looking at a composition, and that's what the chain rule is for. So the chain rule would say that df dt is del f del x del x dt plus del f del y dt, dy dt, plus del f del z dz dt. So we'll just work out these individual values. To work out the dels, we'll just take the function f and we'll differentiate it with respect to the different values. So the derivative with respect to x will require the chain rule. It's the derivative of the first, y squared, times the second, e to the xz, plus the first part, xy squared, times the derivative of the second part, e to the xz, times the derivative of the argument with respect to x, which is z. The derivative with respect to y, well, the x, e to the xz as a constant comes along for the ride, and the derivative of y squared is 2y. And finally, the derivative with respect to z is just going to be, well, see, the xy squared comes along for the ride. The derivative of e to the xz will be e to the xz times the derivative of the argument, which is x. On the other hand, the dx dt, dy dt, dz dt can be found by these formulas here. The derivative of x with respect to t is 3, the derivative of y with respect to t is minus 1, and the derivative of z with respect to t is t squared. Or sorry, it's 2t. And so we'll add these up, and we'll have our derivative formula. We can clean this up ever so slightly. If I distribute the 3 through, we're going to have 3y squared times e to the xz plus 3 times xy squared z e to the xz minus 2xy e to the xz plus 2t x squared y squared e to the xz. Now, if the problem was just to work out the derivative, then we would need to go and plug in the explicit formulas for x, y, and z so that our answer was in the variable t. However, the problem wants us to plug in time equals 1. So if we plug in time equals 1, well, what will we get here? Well, when time is equal to 1, that means that x will have to be 2 plus 3 or 5, y will have to be 6 minus 1 or 5, and z will have to be 1. So we can plug in the values t equals 1, x equals 5, y equals 5, and z equals 1. So we're going to have 3 times 5 squared times e to the 5 times 1 plus 3 times 5 squared times 1 times e to the 5 times 1 minus 2 times 5 times e to the 5 plus t times 2 times t, which is 1, times 25, 5 squared, times 5 squared, times e to the 5. So what will that give us? Well, here we're going to have 3 times 25, or 75 e to the 5. Next, 3 times 5 times 25 is 375 e to the 5. Next, 2 times 5 is 50 e to the 5. And then we have 2 times 5 times 5 times 5 times 5, which is 1,250 times e to the 5. So if we combine these values together, we get a grand total of 1,650 times e to the 5. And so there would be our derivative evaluated at the point 1. There is a variation on the chain rule that pops up quite a bit. Suppose you had a function of several variables, say a function of 3 variables, x, y, and z. And let's say that each one of the x's, y's, and z's are themselves functions of several variables, which I will call a, b, and c. Now you might be asking, when would such a thing happen right here? Well, you might remember that in topic 2, we talked about the different coordinate systems you can use for R3. X, Y, and Z is one type of coordinate system, but there are other ones, such as spherical coordinates. In this case, we've been able to write X, Y, and Z as functions of a rho, a theta, and a phi. And the ability to switch between coordinates will be useful to us a little bit later on. And so there's a very natural time when we would want to take input variables in x, y, and z and change the x, y's, and z's into something else. So if we had a setup like this, when we plug in x, y, and z into this equation right here, we're going to get a function whose inputs will be a, b, and c. And so it makes sense to sort of call this f with the inputs a, b, and c, f in the a, b, c coordinate system. And so we could ask, how would you take the derivative of this new function with respect to one of these new variables? We would get the derivative of f with respect to x times the derivative of x with respect to a. Where instead of using d's, I'm using del's because I know that x has more than one variable, but we're just not playing with them right now. Plus del f del y times del y del a, plus del f del z times del z del a. Of course, this would work for the other two variables as well. And so these equations together would describe how to take every one of the partial derivatives of f with respect to the new variables. Together, these are sometimes called the multivariable partial chain rules, because we're dealing now with partial derivatives. If f of xy is equal to x squared y plus y squared, find the partial derivatives of f with respect to its polar coordinates. So right now we have f written in terms of its rectangular coordinates. Its polar coordinates are the r's and thetas. So the problem is really asking us to compute del f del r and del f del theta, where r theta are equal to the polar coordinates. And you might remember that we had conversion formulas for polar coordinates. The x value is always equal to r times the cosine of theta, and the y value is always equal to r times the sine of theta. And so we have all of the things we would need in order to make the multivariable chain rule work. We have f in terms of x and y, and we have x and y in terms of r and theta. So let's just work out our multivariable chain rule. If we want to work out the derivative of f with respect to r, the chain rule says it's the derivative of f with respect to its natural variable x times del x del r, plus the derivative of f with respect to y times del y del r. And so now let's just fill in the blanks. The derivative of f with respect to x, well, let's see, working our way through this formula, the derivative of f with respect to x will be 2xy plus 0 times the derivative of x with respect to r. The derivative of x with respect to r is cosine theta, plus the derivative of f with respect to y. If we differentiate this with f with respect to y, we'll get x squared plus 2y times the derivative of y with respect to r. The derivative of y with respect to r is sine theta. So let's clean this up by substituting in. We're going to have 2 times x, which is r cosine of theta, times y, which is r sine theta, times cosine theta, plus x squared, which is r squared cosine of theta squared, plus 2 times y, which is r sine theta, times the sine of theta. So let's clean this up a bit. We have 2 times r times cosine times r times sine times cosine, so that's 2r squared, cosine of theta squared, sine squared, or sine of theta, sorry. If I distribute this thing through so I can make collections here, we're going to have r squared cosine of theta squared times sine of theta. And we distribute to the second piece, we're going to have 2 times r times the sine of theta quantity squared. Now notice that we have 2 of these pieces, so we can combine them together, and we will get 3r squared cosine of theta quantity squared times the sine of theta, plus 2 times r times the sine of theta quantity squared. And I guess last but not least, we have an r sine that we could pull out if we desired. So we would have r times the sine of theta times 3r cosine of theta squared plus 2 times the sine of theta. And so here would be the derivative of f with respect to the variable r. What about the other variable? Let's take a look at del f del theta. So the chain rule says we'll take the derivative of f with respect to its first variable, x, times the derivative of that variable with respect to theta, plus the derivative of f with respect to its second variable, y, times the derivative of that variable with respect to theta. So we fill in all of the blanks. The derivative of f with respect to x. Well, we actually already worked that one out. This one was going to be 2xy, and this other one, just thinking ahead, is going to be x squared plus 2y, since those derivatives don't change. It's only the new derivatives. What's the derivative of x with respect to theta? Well, it's minus r sine theta. What's the derivative of y with respect to theta? Well, it's r cosine theta. And so now if we substitute in our known values for these things, we're going to have 2 times r cosine theta, x, times r sine theta, y, times negative r sine theta, plus we're going to have r squared cosine of theta squared, plus 2 times y r sine theta, times r cosine of theta. So if we clean these things up, we have an r and an r and an r and a negative, so that's negative 2r cubed cosine of theta times the sine of theta quantity squared. Over here, I'll distribute this piece into both parts. So here we're going to have an r cubed cosine of theta quantity cubed. And here we're going to have a 2r squared times the sine of theta times the cosine of theta. Unfortunately, there's nothing that I can combine here. There are some terms common to all of the pieces, though. We could pull out an r squared from each one of those pieces, and we could pull out a cosine. So if we pull out those from the pieces, we're going to have, from the first piece, a negative 2r sine of theta quantity squared. From the second piece, we're going to have an r cosine of theta quantity squared. And from the third piece, we're going to have a 2 sine of theta. And that'll be it. And so there's our derivative of f with respect to theta. So here's a blast from the past, an implicit differentiation problem from Calc 1. Suppose that y is a function of x defined by the equation xy cubed plus 2xy minus cosine of x equals 0. Find dy dx implicitly. Now remember what the basic idea of a problem like this is. You have an equation right here. And it is possible, if we had enough algebraic chutzpah, to be able to solve this for y and to differentiate it then. But a lot of times the equations are just too algebraically nasty. And so we came up with a technique in Calc 1 that allowed us to go and find the derivative in terms of x and y. And we called it implicit differentiation. So let me remind you of how we attacked this in Calc 1. The basic idea was we took this equation, but we kept thinking of y as a function of x. We didn't know what the formula was, we just knew that it was out there. And so we took the derivative with respect to x of this equation on both sides. Now on the left-hand side, the derivative of this first piece, we'll use the product rule. So the derivative of the first part is 1, the second part is just y of x cubed, plus the first part times the derivative of the second bit. Now the derivative of blank cubed is 3 times blank times the derivative of blank. The blank is the function y, so its derivative is y prime. Next, I can work on this next piece. It's another product rule. So we'll take the derivative of the first piece, 2, times the second piece, which is y, plus the first piece, 2x, times the derivative of the second piece, which is the derivative of y, or y prime. And then finally, I have to take the derivative of cosine of x, negative, which is positive sine of x. On the other hand, the derivative of 0 is 0. So this gave me a giant equation in terms of x's and y's and y primes. Let me clean it up a bit. We get y prime plus 3x y squared y prime plus 2y plus 2x y prime plus the sine of x is equal to 0. Notice that exactly 2 of these pieces have the y prime in it. So I'm going to move everybody over to the other side of the equation. So we're going to have a negative sine of x. We'll have a negative 2y. We'll have a negative y cubed. And then the stuff that's left on the left-hand side has a y prime that can be factored out. So I can have 3xy squared plus 2x times y prime. So now I could simply solve for y prime by dividing both sides by the expression 3xy squared plus 2x. And on the top, I'll just pull that minus out, and we'll have negative sine of x plus 2y plus y cubed. And so we call this expression the implicit derivative. Do you remember doing a problem like this in Calc 1? Do you remember hating it in Calc 1? It was a weird application of the chain rule. Well, it's still an application of the chain rule, but we're going to make it much simpler. Because if you look at the equation I've circled, the left-hand side just screams function of 2 variables. So we have a function of 2 variables who we've set equal to 0. So let's go and use the chain rule to take the derivative of the left-hand side. Right, the chain rule would say that if x and y were themselves functions of some extra variable, then the derivative on the left-hand side with respect to that variable would be the derivative of f with respect to this variable would be the partial derivative of f with respect to x times the derivative of x with respect to this variable plus the partial derivative of f with respect to y times the derivative of y with respect to this variable. And that would equal 0 because the derivative of 0 is going to be 0 no matter what variable we pick. But remember, we're trying to solve for dy dx. So if I stuck x's in here, x is obviously a function of x, it's himself, and y is a function of x. That's the whole point of the problem. It's an unknown function of x. And so the chain rule, the multivariable chain rule says that del f del x dx dx plus del f del y dy dx is equal to 0. Well, let's fill in the blanks here. What is the partial derivative of f with respect to x? Well, it's going to be y cubed plus 2y minus negative the sine of x times the derivative of x with respect to x. Well, the derivative of x with respect to x, that's 1. It's dx over dx. It cancels. On the other hand, we have the derivative of f with respect to y. So that would be 3xy squared plus 2x plus 0 times dy dx, which is what we're looking for, and this is set equal to 0. Now I'm trying to solve for this thing right here. But look at how easy that is. Move this piece over. We'll get 3x squared plus 2x times dy dx is equal to negative sine of x plus y cubed plus 2y. And then we'll divide both sides by this expression. And voila, the exact same implicit derivative. Near the point 6 minus 3, 2, the surface z times the sine of x plus zy equals 0 defines the graph of some function z equals f of xy. Find the gradient of this function f at the point 6 minus 3. So the problem wants us to work out the gradient of the point 6 minus 3. That means we want to work out the vector whose first component is the partial derivative of x at the point 6, 3, and whose second component is the partial derivative with respect to y at the point 6 minus 3. So how will we get these partial derivatives? Well, the only equation I've got is this right here, sine of x plus zy equals 0. And what I need to do is I need to be able to solve this so that z is equal to some formula in x and y. Unfortunately, this equation is just far too difficult for us to be able to solve right here. However, imagine we were to treat this whole thing as a function of 3 variables. We could then apply the chain rule to it. If we applied the chain rule to it, we would get, for any variable we picked, the derivative of w with respect to that variable is equal to the derivative of w with respect to x times the derivative of x with respect to that variable, plus the derivative of w with respect to y times the derivative of y with respect to that variable, plus the derivative of w with respect to z times the derivative of z with respect to that variable, and this would have to equal the derivative of 0, which is 0. Does this help me out here? Well, think about this. Z is supposed to be a function of x and y. It's hidden in there. That means that the partial derivative of f with respect to x would just be del z del x. That's one of the sets of symbols we use right here. So if I were to take the variable x and plug it into these 3 spots, I could actually solve for del z del x. Even better, the derivative of x with respect to x is just 1. And the derivative of y with respect to x, remember x and y are variables. If you take the derivative of y with respect to x, you should get 0, because y is a constant from x's point of view. And so this actually boils down to the equation, the derivative of w with respect to x plus the derivative of w with respect to z times the derivative of z with respect to x is equal to 0. Or if you'd like, the derivative of z with respect to x is equal to negative the derivative of w with respect to x divided by the derivative of w with respect to z. So we could work out this partial derivative, and then we could plug in the point 6 minus 3, 2, and see what we get. Well, let's give it a shot. So we'll have the derivative of z with respect to x is negative the derivative of w with respect to x. If we differentiate this with respect to x, as z comes along for the ride, the derivative of sine of blank is cosine of blank times the derivative of the inside, which is 1. If we differentiate this with respect to z, we're going to have to use the product rule. So we'll have the derivative of the first times the second plus the first part, z, times the derivative of the second, which will be the cosine of x plus zy times the derivative of x plus zy, which is y. So now, if we were to go and plug in all of our specific values, x is equal to 6, y is equal to negative 3, and z is equal to 2, we're going to get 2 times the cosine of 6 minus 6 divided by the sine of 6 minus 6 plus z times y is negative 6 times the cosine of 6 minus 6. Now, sine of 6 minus 6 is the sine of 0. That's 0. The cosine of 0 is 1. And so this is going to become negative 2 over negative 6, or 1/3. And so we've found this derivative, the derivative of f with respect to x, without actually finding f first, which is really quite amazing. Now, we could repeat the exact same argument. If the derivative of z with respect to x is the opposite of the derivative of w with respect to x divided by the derivative of w with respect to z, then by symmetry, the derivative of z with respect to y should be negative the derivative of w with respect to y over the derivative of w with respect to z. Now, we've already worked out the bottom term already as being the sine of x plus zy plus zy times the cosine of zy, or x plus zy, sorry. On the other hand, if we differentiate our function w with respect to y, z comes along for the ride, we're going to get cosine of x plus zy times the derivative of x plus zy with respect to y, which is z. So now we'll plug in our point, 6 minus 3, 2, and this will come out to being negative. We're going to have a z times a z, which is 4 times the cosine of 6 minus 6, all over the sine of 6 minus 6, plus z times y, which is negative 6 times the cosine of 6 minus 6. Just like last time, cosine of 6 minus 6 is 1, sine of 6 minus 6 is 0, and so this will give us a grand total of negative 4 divided by negative 6, or 2/3. And so, we found another partial derivative without knowing the function we were differentiating first. And so here's our answer, obtained almost by voodoo magic, but really by the chain rule.